Alright, so let's do a few exercises in the section. So let's pick number 10. So in number 10, the matrix is equal to 3, -1, 1, 1. The goal is to try to diagonalize this matrix. So first we solve the characteristic equation, which is the determinant of a minus lambda I equal to 0, which means the determinant of 3 minus lambda, -1, 1, 1 minus lambda equal to 0, which implies 3 minus lambda times 1 minus lambda plus 1 equal to 0. So this gives you lambda squared minus 4 lambda plus 3 plus 1 equal to 0. So lambda squared minus 4 lambda plus 4 equal to 0. So lambda is 2. So we have one eigenvalue. So we need to see if there are two linearly independent eigenvectors correspond to this eigenvalue. So now we want to solve a minus 2i times v equal to 0, which gives you 1, -1, 1, -1 times v equal to 0. So in this case, the solution is 1, 1. So only one eigenvector. But because A is a 2 by 2 matrix, so we will need two linearly independent eigenvectors for A to be diagonalizable. So this tells us that A is not diagonalizable. Okay. Right, so let's look at example 16. So A now it's a larger matrix. 3, -2, 0, 0, 1, 0, -4, 4, 1. So same thing, we have to first solve the characteristic equation, which is determinant of a minus lambda I equal to 0, which means determinant of 3 minus lambda, -2, 0, 0, 1 minus lambda, 0, -4, 4, 1 minus lambda. Second row has a lot of zeros. Let's do that. This is a plus. So this means 1 minus lambda times the determinant of the, cross these out, of 3 minus lambda, 0, -4, 1 minus lambda equal to 0. Oh, this one is not bad. It tells you directly that 1 minus lambda times 3 minus lambda times 1 minus lambda equal to 0. So there are two eigenvalues. First one is 1, and the second one is 3. Okay. So let me see if I can fit into the space here. So for eigenvalue 1, we want to solve a minus I times v equal to 0, a minus I, so we want to solve this thing. A minus I is 2, -2, 0, 0, 0, 0, -4, 4, 0. So we want to solve this thing times v equal to 0. Notice that the third row is the same as the first, pretty much the same as the first row, so it doesn't count. The second row is all 0, so it doesn't count. So all the conditions we have is that 2v1 minus 2v2 equal to 0, which means v1 is equal to v2, and v3 is free. So we have two free variables. So the solution equals to v1 equal to v2, let's say equal to t, and v3 is free, it's called s, so we have t, t, and s. So it's 1, 1, 0 times t plus 0, 0, 1 times s. So we have two linearly independent eigenvectors corresponding to this eigenvalue. So this is our v1, and this is our v2, corresponding to the eigenvalue 1. Now, For the eigenvalue 3, we want to solve a minus 3i times v equal to 0. So we want to solve 0, negative 2, 0, 0, negative 2, 0, negative 4, 1, 1 times v equal to 0. Second row is not doing anything because it's the same as first row. The first row tells you that the second coordinate is equal to 0. And the third row tells you that negative 4v1 plus v3 equals to 0. So v3 is 4v1. So the solution is v3 is 4v1, so v1 is so it's 4v1, v1, and 0. So this is equal to 104 times the constant. And this is our third eigenvector. So since we have three linearly dependent eigenvectors, so A is diagonalizable. So A is equal to P dP inverse. P is the matrix with eigenvectors being on the columns. So 1, 1, 0, 0, 0, 1. This is the first two eigenvectors. And the third eigenvector is 1, 0, 4. This is the third eigenvector. And D is the diagonal matrix with diagonals being their corresponding eigenvalues. So the first two eigenvectors correspond to eigenvalue 1. So the first two diagonal entries are 1, and the third diagonal entry is 3. Oh, it should be green. All right, so let's do a proof practice. So let's do 29. Ask you to prove if A and B are similar and B and C similar, then A and C are similar. So this is following the definition of being similar matrices. So let's do that. So the fact that A and B are similar means A equals to P times B times P inverse, where P is invertible matrix. And the fact that B and C are similar tells you that B is equal to, let's say, Q times C times Q inverse. Q is invertible. Well, B is equal to this. Let's plug this into here. So we get A is equal to P inverse, Q, C, Q inverse. And now let's recall that Q inverse, P inverse is PQ product, the whole thing inverse. So the order is reversed here. So A is equal to PQ times C times PQ inverse. Therefore, by definition, so A is equal to a matrix times C times the first matrix's inverse. We can say this is equal to R times C times R inverse, and R is equal to PQ. So therefore, A and C are also similar. Alright, so let's do another exercise. Let's do exercise 32, which asks you to prove if A and B are similar, then A and B have the same characteristic equation. Okay, so let's do that. Same thing. Let's first translate the definition being similar. So A and B are similar means A equals to P times B times P inverse, where P is invertible matrix. Okay. So let's recall the characteristic equation for A is the determinant of A minus lambda I equal to 0. So this is the characteristic equation for A. But we can plug this in. So A, we know A is PBP inverse, so we can plug it in here. So we get determinant of PBP inverse minus lambda I equal to 0. So here we use a tiny trick. We use the fact that I is equal to P times P inverse. So this is P times P inverse equal to 0. Okay. So notice lambda is constant, and then these two terms have common factors. So they both begin with P, they both end with P inverse. Let me rewrite it. So this is determinant of PBP inverse minus P times lambda times I times P inverse equal to 0. So we can factor the P out from the front, we can factor the P inverse out from the back. So this is equal to determinant of P, let's use green, P times B minus lambda I times P inverse equal to 0. And we know determinant is multiplicative, so this means the determinant of P times the determinant of B minus lambda I times the determinant of P inverse equal to 0. But we know determinant of P and determinant of P inverse are reciprocals. So they cancel each other. Determinant of P inverse is 1 over determinant of P. So they cancel each other. So we get, and we're done here, we get determinant of B minus lambda I is equal to 0. And this is the characteristic equation for B. So A and B have the same characteristic equation. And because they have the same characteristic equation, then that means they have the same eigenvalues. Because eigenvalues are determined from characteristic equations. Alright, so that's it for section 6.2. We'll be talking about applications of diagonalization in the next section.